Hello, and welcome to Business Calculus Composite Functions. The development of our differentiating skills is nearly complete. The remaining element is how to differentiate composite functions, two or more functions that have been chained together. If we look at the function capital F of x equals the square root of the quantity x plus 2, we see that this function is x plus 2 plugged into the square root function. What we'd like to do is learn how to recognize composite functions, be able to break them up into their components, and then be able to differentiate the components individually. We say that a function m is a composite of the functions f and g if m equals f of g. The domain of m is the set of all numbers x such that x is in the domain of g and g of x is in the domain of f. Here we have a schematic drawing illustrating what we mean. If we have some point x that starts over here in the domain of the function g, which is the big circle, we have that the domain of m is some small subset of that. The function follows the composition and goes through a chain, jumping into the range of g in the domain of f, and then finally into the range of f over here, or it follows the path of the composite m, making the jump in one step. So the bottom part represents the chain that we're talking about, and thinking of the one function m as the composition of two functions f and g gives us an ability to evaluate its derivative. Let's look at some examples of composite functions so that we get better at recognizing them, and that will allow us to move forward with our differentiating skills in further videos. So we're going to take the function f of u equals eu and the function g of x equals negative 4x and write the following compositions. So first off, we're going to take f of g, which means that we write down our function f, and then we're going to plug into that function wherever u appears the formula for g. So we now replace g of x with its definition, and we get that this composition is e to the negative 4x. Next up, we're going to do the composition in the other direction, where we take g of f of u. So we write down our function g, and then we are going to replace its variable x with f of x. F of u, excuse me. Then we replace f of u with its definition. So we get negative 4e to the u. All right? The more important skill is when we do this backwards, when we take one function and break it up into its components. So looking at our first example, y equals the square root of 3 minus x squared, we see something similar to our earlier example where we have some function plugged into the square root function. So what I'm going to do is I'm going to write the square root part in black, and I'm going to write the interior part in blue to make it easier to see what we're thinking of as our two components. So we're going to break this up into y equals f of u, and then we're also going to write u equals g of x as our two components for our function. F of u is going to be equal to the square root of the function u, and g of x is going to be 3 minus x squared. And we can see using the colors here the two components of our original function y. Let's do that for one more example. We have y equals 50 times e to the 0.01x power. And what we would like to do is figure out a way to represent this as the composition of two functions. So my first function I'm going to think of as 50 times e to some power, and then that power is going to represent the inside function of my composition. So again, breaking this up into two parts, y equals f of u, and u equals g of x, we're going to have y equals 50 times e to the u, and then for our second part, g of x equals 0.01x. All right, what I would like for you to do is to take this example, y equals the cube root of x squared minus 1, and write it as the composite of two functions. Here are your choices. Thank you very much for listening.